of Michigan. He got his PhD in 2020. After that, he went to the University of Washington to pursue his postdoc work with Nathan Katz. And his research interest is focused on the interaction among deep learning, operator theory, and fluid dynamics for reduced order modeling and control of complex nonlinear dynamic systems. So for today's talk, Dr. Shaowu Pan will present a work called the NIF, or Spatial and Temporal Representation, Learning Paradiagram Beyond POD and CNN. So let's welcome Dr. Shaowu Pan to start his talk.
Thank you, Professor Zhang, for the warm introduction. Today, I wanted to talk about neural implicit flow as a mesh-agnostic representation for learning paradigm of spatial-temporal field. And this work is collaborated with Steve Brunt and Nathan Cooks at the Department of Applied Math at the University of Washington. So the untold motivations actually it was back in 2019 when I was visiting, visiting University of Southern California, and I have a friend over there, Xiangyu, and he's supervised by Professor Ian Marino, Benjamin Marino, and at that time I was asking Xiangyu, like, I want to ask for some fancy data for my fancy Kuman framework. And Xiangyu gave me the framework, and it's a fancy shock-induced ignition problems. So I'm excited. I downloaded the data set and took a few gigabytes. Well, but he never told me it was an AMR. So at that time, I feel embarrassed because the when you want to do anything like model analysis or reducer modeling, especially right now in data-driven modeling community, as everything you do, you need to first do a POD. Most of the time, unless you use a CNN. But for these problems, you can still do CNN, but you need to chopping down. As you can see, there's so many fine vortices over there. So it is best to use adaptive if you can find a method that is appropriate and fits well for adaptive mesh refinement. Than using POD methods or CNN method, because POD requires I fixed the mesh at all times. So at that time, I was feeling really embarrassed. That's the moment I realized data-driven, for this community lacks proper treatment for dimensionality reduction for data on arbitrary mesh. We cannot play on it. This is kind of toy data set anymore, and that's why it's sort of placing a seed inside of me that I want to figure out this problem one day. So fluid systems contains a large spatial degrees of freedom. This is how it distinguishes, a fluid system from typical nonlinear dynamic system. If you ever talk to a control people, control people are going to say, oh, fluid system is governed by partial differential equations, so it's infinite dimensional. Therefore, my methodology won't work on your problems. But however, it's not really true that fluids are not necessarily infinite dimensional. It's just having a large degree of large spatial degrees of freedom. And if you can sort of reduce the degrees of freedom, either using like traditional method of POD or CNN or other fancy methods, then you can leverage those modeling and control techniques from those communities to apply to fluid systems. Therefore, the goal is to reduce the spatial degrees of freedom. This is actually usually the first step if you do any kind of data-driven methods, because interpolations, playing around with all those machine learning techniques, usually it happens in low dimensional space. So this method is usually categorized as dimensionality reduction. The state of art is basically two methods. The first one is POD, using the SVD algorithms. Usually it requires it's introduced by Lumley in 1965 to our community. Originally it's KL expansion methods from the statistic community. So I wanted you guys to pay attention here is that a POD requires a single fixed mesh, and because it's flattening these values on this mesh and stacking for all time steps. Then you perform some sort of SVD to obtain like U as V transpose, then the V transpose, is a much fat matrix, and it is basically what we call the latent representation of this fluid system. The second one is convolutional neural network. It is mainly proposed by Yang Kun around the 80s. And I want you guys to pay attention here is that the CNN requires a uniform pixelization of your original images. It might be good for like computer vision task or for recognizing cat and dogs or maybe even humans, but not really that suitable for film mechanics because, we always have, multi-scale phenomena randomly at some places in the fluids. So therefore, uniform pixelization is not really a good way to process in the data set. But this has been state of the art in the data-driven for a fluid system, I guess, in the past 5 years. Really large number of papers. If you go look at them, every single paper is starting with a CNN in a rectangular mesh. However, this is not really appropriate for turbulence, and especially for wall boundary turbulence, for example. So let's look at the data structure in the real world of CFD. It's not really like it's going to be really complicated. For example, you can have adaptive mesh for aircraft where those eddies are chased by those meshes, and you're going to have some sort of parametric variation of the meshes. For example, if you are doing some sort of surrogate modeling and your design variable is the pressure ratios over there, as you can see, when you're changing the pressure ratios, the physics is going to change. And for this problem here, the shock physics change a little bit and the shock location is changing. Usually, normally, if you're running hypothetical simulation, you probably want that you have the mesh adapted to the shock locations. Therefore, the mesh going to be changing across different design parameters. So these all sort of imposing challenging questions for PUD and CNN. So it would be difficult for them to handle like parametric varying mesh topology and adaptive meshings. Or problem with multi-scale, multi-resolutions is also very difficult for, like, for example, CNN. And if you want a scalable nonlinear 3D dimensionality reduction, CNN is also not possible. The reason is I would say it's really challenging because when you're jumping from the 2D CNN to 3D CNN, the memory requirement jumps from quadratic to cubic. And this is why, this is causing a lot of issues for 3D CNN to work. For example, if you're using the largest GPUs and apply the 3D CNN, you'll find that the best highest resolution I can find in a paper is 64 cubic, which is barely any turbulence. And therefore, we need to have something new. We need new solutions for the data structure in the real world of CFD. So this is how I propose the neural implicit flow as a third generation paradigm. So neural implicit flow basically contains like two networks. One of them is like what I call a shape net with spatial coordinate as input. The other one is called parameter net with any other factors that is not spatial coordinates will be feeding as into the parameter net. And the output of the parameter net will be like having a bottleneck layers over there, probably just like less than 10 units. And then these 10 units will mapping with a linear layer, mapping to all the weights and biases of the shape net. So for example, if the shape net inside is just a simple feed for a neural network, and the parameter net is also a simple feed for a neural network. So it is the simplest case. And for example, if the shape net has these structures, like for example, 3, 10, 10, 10, 1, you probably end up with like 6,000 parameters. Then you will have, you're probably going to have a linear map that mapping from 3 to 6,000. And then once you will have this output as you basically determines you basically is the output that at this XYZ and at this external parameter, for example, time. So then you want to fit the U to the ground truth data using gradient descent, and then you want to optimizing this network As you can see, this framework, basically what it does, it only takes 0.1 sampling. Therefore, it can be used for any kind of meshes. For example, here on the left, as you can see, this data is adaptive mesh refinement data. So normally, CNN and POD won't really work that well, as we will see in a minute. So another important thing to notice here is in this focus. So when I'm training this my new implicit flow, it's just a very simple supervision learning problem. What it does is just make sure the U minus the U true, the mean square error between U and U true, and just minimizing that. And by optimizing all the weights and biases in this parameter net, because anything in the shape net is determined by the parameter net. So there's nothing to optimize in the shape net. Other thing you need to optimize is in the parameter net. And there's a big linear layer over there. So this is other thing you need to optimize. Once you train this network very well, so for example, if you evaluate this with all kind of XYZ and you find this reconstruction is pretty similar to the original data, then the latent representation is basically hidden here. So for example, so latent representation basically telling you how to describe this spatial field at this time or this instance of parameter, because we're reducing the spatial degree of freedoms in, we're reducing the spatial degrees of freedom. So everything else is, so should be embedded in these units right here. So another way to think about this new implicit flow is that if I have like a spatial temporal field at this time, so it's just only a spatial field. And to determine this spatial field, all I need is the weights and biases of this shape net. Then I can determine this spatial field with infinite resolutions, right? Because it just is a function and I can evaluate anywhere. You can also think about this, like I have a straight line, if I have a 100 point on a straight line, it's just 100 points over there. But what really determines the straight line is just two parameters, the skewness and the bias. So this, if you think about this in a neural network sense, then you'll figure out why I introduced this shape net right here. Okay, so the take-home message here is that it enables mesh-agnostic representation of spatial temporal fields. And another thing to notice is that the model complexity only scale with the complexity of the signal itself, rather than being affected by all those meshes. So comparison, I want to do a little bit comparison with other machine learning PD framework. Although for my framework, I'm not really like working on doing learning a surrogate model for a PD solver, but I just want to make a comparison so you can see some interesting connections over there. So on the left, as you can see, this is our new implicit flow I just described before. On the right, you can see this is a famous depot net proposed by Professor Johnny Karnidakis group. And here, as you can see, there's some similarity between this framework, and you see like you can actually see some differences as well. So the depot net basically is to, if I make sure that the parameter net is only fitting the last layer of shape net. So on the right hand side over here, I just make sure this is a free-form neural network, and the last layer of the free-form neural network, the weights over there and biases, it is determined by the parameter net, and there's no bottleneck over there. Then you can see that the skeleton of depot net is a sort of a special case of neural implicit flow, because this is pretty evident over here. And another difference is that the neural implicit flow takes a really, what we're doing is doing a learning representation for spatial temporal data set, rather than learning a function, mapping from function to functions. Another one is neural operators, which is pretty different from these above two algorithms. What it does is mostly working on a graph, and on this graph, they use message passing to emulate the convolutions of the CFD, the convolution operations when we, if of the analytical solutions of the PDE. So for example, if the problem is linear, if the PDE is linear, then you could use Lagrange function to find analytic solutions. A neural operator is basically exactly neural network emulations of that process. And but however, it's not really that connected to the above two algorithm, but I want to pinpoint there's big difference over there. However, and next thing I want to talk about is I want to give a detour onto a little bit a quite hot topic in deep learning communities in 2 years ago. It is about learning versus approximating. It has been shown that neural network can approximate any kind of sort of normal functions, but it only tells you about the existence. So given the number of errors you can tolerate, you can always find possible combinations of weights and biases to fit this function given this number of error. However, with the gradient descent for a non-convex problem, we actually don't know what we're going to get at the end of the days. And this is actually a very interesting phenomenon that is point by Professor Xu at Shanghai Jiao University. So this phenomenon is called the frequency principle in field for neural network. So they found out that neural network tends to fit low frequency signals first, and sometimes it takes infinite amount of time to fit high frequency contents. However, for our problems here, the turbulence is sort of a high wave number spatial. It contains sort of high wave number spatial signals because it contains so many small scales. So when we're applying these kind of the framework before to turbulence, it's going to have some issues over there. So one idea to solve this problem is to use a hard-coded multi-scale features. The paper is called Fourier. Basically, what you do is when you're having this x, y as your input, the spatial coordinate as your input, you're trying to pre-process these features x, y by giving them some sine, cosine features. Then from there you're trying to fit these fit the outcome, for example, the images over there. And if you do that, you see you can find a much better performance than if you don't. So the top row over there is the result. If you don't apply anything like hard-coded features, you will only learn the low frequency signals, and no matter how long you train the network. So so for example here you can see on the if you are going to fit an images over there. Let's say using the X and Y as the input, then output is RGB of the images. On the left is basically if you use a vanilla fit for a neural network and to fit these images. On the right, it is basically what you're going to get if you're using hard-coded multi-scale features. As you can see, the performance, there's a significant difference in the performance over there. So I want to pinpoint here that I recall there's a famous framework from George Karadakis' group called a physics-informed neural network. The physics-informed neural network also takes like spatial or time coordinates into a neural network, and it outputs basically the field of interest, for example, the U, and the U follows the follows the partial differential equations that you know. So, and you're minimizing the residuals, and based on some collocation points, then you're trying to find the solutions from this PDE. However, so this actually is problematic. This phenomenon is problematic for pins as well, as pinpointed by Paradakis' group at the University of Pennsylvania, that if you do not using any kind of fancy these kind of techniques, the pin will only trying to solve low frequency features of the flow. Therefore, it won't be really that suitable for turbulence. This is why they believe, and also I believe, this is a major reason why physics-informed neural network still is quite challenging you apply to really turbulent flows. And then, by the way, Sifan Wang and Paris, they also applied this framework and did a little bit of modifications and apply on the pin. However, in practice, I find that if you're using the hard-coded multi-scale features, the results really depending on how you're choosing the scale of the sine waves. And therefore, I choose another approach, which is using sine activation functions. So this is a famous work from Stanford, I believe. It's called implicit neural representation of with periodic activation functions. What they did, they're using these sine activation functions, but the sine activation function has been used in the history as well. Their major contribution is to develop a novel initialization scheme so that you can train this network really well. But basically what they do is, same as before, they put X, Y as your input of your neural network, and the output is the gray the gray cloud point of these images, and then you can see the siren basically is their framework and performs best and converge much faster than if you're using other activation functions. And we adopt this module in our framework to learning the representation for turbulence. Okay, so this is basically the modules that we are using here. So we're using we put the X, Y, Z as our input, and we having a linear layer over there, and we scaled it with a constant factor, which is like just 30, and then we put it using sine activation functions. Then we have a residual block over there contains like basically it's a ResNet-like feature blocks, not necessarily the original version of ResNet. And then we repeat several times, we output the final quantity of interest. So the first text I want to give using our framework, the first application is an autoencoder for adaptive mesh refinement. So as you can see here, this is really tailored instability problems, and the data is obtained using Castro, which is adaptive mesh refinement solver. And you can see if I take like two, the ground truth, dimension for this data set actually 1, because I'm only sampling 1 trajectories. So the flow field never repeat again. That's why the underlying dimensionality should be 1 because it's time. If I take like rank 2, because I want to visualize the POD much better. So as you can see, the POD would at the same number of ranks, using same number of rank 2 as against any other frameworks. It's sort of blurry around the front of these material interfaces, which is not really pleasant. However, for CNNs, if we take a closer look at this, we found that the CNN really requires a pre-processing, and that pre-processing really determines the quality of your autoencoders. And if you're using like NIF, you don't really need any kind of pre-processing. You're just using point-wise data set, and you can learn a low-dimensional representation of this flow field. And note that this flow field is contains some multi-scale there. Performs the best. And so how do we construct this autoencoders? So because the NIF framework is sort of like a decoder, not really an encoder. So therefore we need to manually choosing how do we feed informations into to getting a latent representation. So just like autoencoder over there. So the way we do is basically we put 32 sensors along the sort of the y-axis of the middle y-axis over there. And then we're using these 32 sensors as our input to basically determine which flow state the flow is currently experiencing. And you could use maybe convolutional neural networks or any other techniques, or maybe for your problem, you want to randomly choosing some sensor points. As long as these sensor points, the number of sensors is larger than the ground truth dimensionality of the flow, then you are okay. So next, I want to give a detailed comparison about non-implicit flow versus POD and CNN. So POD and is really, it's actually, in terms of resolutions, POD and non-implicit flow is both really good because POD, if you have a single fixed mesh and if you're using all the modes, POD definitely gonna converge to the ground truth data set. While new implicit flow, it requires a gradient descent training process. It might be a little bit slower. It can be slower than the Performer 2, but once it's trained, it has really high resolutions, and actually sort of infinite resolution because it's a continuous field. You can evaluate at as much any kind of fine resolution you want. However, the CNN is pretty weak in terms of resolution because it requires a uniform mesh. In terms of complex geometries, the POD can working with complex geometry, but not varying geometry. However, CNN is a little bit weak because if you have like small geometry features near the CNN, this pre-processing with uniform mesh won't catch it at all. However, it's not a problem for new implicit flow because it's training in point-wise. In terms of scalabilities, POD is actually pretty strong. If your problem is really nice and the grid is nice, so you can use a lot of algorithms available. For example, parallelized SVDs or randomized SVDs. They're very available. However, for CNNs, it's okay in 2D but very expensive in 3D. If you're doing like 3D turbulence in really industrial level, CNN won't be the one you really want to use. However, new implicit flow has no such issues. It has no such issues in terms of scalability because there's not much differences when you're jumping from 2D to 3D, except you need just longer training time. But for CNNs, because of memory issues, you won't be able to train if you're having a really high resolution data set in 3D. So in terms of parametric and temporal variation of domain dispositions, obviously, as I have mentioned many times before, new implicit flow outperforms the other two MAC algorithms in these categories. In terms of training easiness, POD is easy to train and easy to code. CNN is kind of fair, but new implicit flow, it takes much longer time actually training than CNN and POD. However, for some problem, new implicit might be the only way. In terms of interpretability for the representations, POD is kind of strong because you're always going to end up with, it's not a gradient optimization process, so you always end up with the same basis for the same data set. So there's not much randomness over there. So you can, and it's a linear basis, so you can have some interpretability over there. For CNN and new implicit flow, as for CNN, it's kind of pretty weak because it's nonlinear everywhere. But for new implicit flow, I point out fair here because if as I will show later that if I actually did last layer parameterizations, it just learns the linear subspace. So it sort of performing a proper decomposition on adaptive mesh refinement. So you will still have some interpretability over there. In terms of expressiveness, obviously POD is a linear algorithm. So it's, and there's been many papers have been shown that POD is not really ideal for adaptive action dominated flows. For CNN, it's actually pretty fair. I think it's nonlinear. For new implicit flows, I point out strong here because of the expressiveness. I believe it is nonlinear framework, and it also has ability to capture multi-scales. So this is how I pinpoint it's strong versus the CNN. And the second task would be maybe a more popular task is basically performing a mesh-agnostic data fit surrogate models. So there has been many surrogate models right now in the market. There's physics-informed based on projection-based reducer models. However, the one I'm going to tell here is perhaps the most naive one, but also most widely used one, and especially in industry. So it's just performing what it does. It just giving me the time and the system parameter mu. I just want to know what is this PD solution at this time and mu. I just want to know the spatial solutions over there. So it's just a black box models, but it will at online time it can be inferenced really fast. So it will be helpful if you really want to use in situations with many queries problems, for example, optimizations or controls, and especially if you want to do real time, I think data fit model is probably the only way. in terms of inference, because for other kind of physics models, you need to run some sort of physics solver in the background, some sort of, so it will take more time. So as you can see here, I'm running a 1D parametric Komodo-Shevchinsky problem by varying the mu over there, the basically viscosity in the equation. And you will find that when you vary the mu over there, you will see pretty interesting phenomena. That so here is the space-time plot of the solution field. You can see that when I'm changing the system parameters, the solution changes from periodic oscillations to traveling waves. And the time you takes you to traveling waves also changes. And at some point, you don't really have this, oscillation transitions over there, you just directly jump into traveling waves. So it's pretty a lot of interesting, parametric variation of the PD over there. And when you are doing these kind of data fit surrogate models, a very naive idea is just takes XYZ T mu for a single neural network, for the input of a single neural network and output U. You can think of this physics-informed neural network, but it's not using the physics information, it's just a surrogate model using the skeleton of physics-informed neural network. So how does that perform versus my neural processor flow? So as you can see here, it's interesting to see that neural processor flow generalizes better in this problem than the simple MLP with smaller model complexity and less training data. So when you're having the same number of training data points, the NIF always performs better, generalized better than the MLP approach, just like sort of the physics not informed neural network. For the if you're having the same model parameters over there, NIF also generalized better than MLP here. So next text I want to talk about is remember the previous slides. There's a table over there, and I talk about the interpretability of neural processor flow. So here is like one example over there. So here I did a little bit of modification to the original neural processor flow framework, where I only use I only make sure that the parameter net determines the last layer weights of the shape net. So all the other formal layers before the last layer is just another optimization variable that you need to figure it out using gradient descent. And here, if you're doing this and you put time t over there, and you will figure out that what it does, just look at the last layer, the equation for the last layer will be rank 1 summation of the flow of the spatial temporal field, and each term in the summation will be like a term determined only by time multiply a term only determined by space. So it's really much similar to proper orthogonal decomposition. However, the difference here is that we do not enforce orthogonal conditions over there, because for most of the tasks in data-driven modeling community, when we're doing POD, what we really need is decomposition, not the orthogonal. We need the D, not the ZO. If you can get in the linear subspace, you can do POD, you can do control, you can do really a lot of stuff over there. And this is why I proposing this framework. And as you can see here, I take a data set from, I think from another adaptive measurement solver called Pele, and developed by Livermore National Lab, I believe. And the data set over there is a flow of a cylinder, very simple data set. However, the mesh is adaptively changing at each time. And what if right now I want to do a DMD task over there? Then you using this framework over there, and you're training on this data set, then you will find out that if you evaluate in the time t at at a certain time, you're getting this coefficient A1 to AT, right? Then you plot it over there. So there's basically 10, in this problem, the last layer has 10 weights over there. So then you can plot them all over there. You will see like 10 lines. And note that this timeline is basically representing the time variation of this of this spatial temporal field. So you can just using this 10-dimensional time series to perform DMD. Then when you perform the DMD, you get qualitatively very similar results if you're getting from the original DMD if there's no adaptive mesh refinement, if the grid is much simpler. So the significance of this task is that if you still prefer to do any kind of PUD-ish modeling on arbitrary meshes, you can use this framework to do that because it only gives you a linear subspace. Okay, so next test I want to give is compressing a 3D homogeneous isotropic turbulence over here. So here, because this fitting task, so basically this task is, I just want to have XYZ as input and using time t as, as input for the parameter net. And I'm going to only have, like, for example, like 3 units over there, or maybe 1 unit over there, learning sort of a latent representations for this 3D field. Because once I determine these 3 units over there, I multiply this big linear layer over there, I getting the weights and biases at this time step for all the spatial, all the, turbulence instance over there. This fitting test is actually nearly impossible for 3D CNN on a single GPU card because of this cubic scaling of the memory. So 128 cubic is basically impossible for like 3D CNN if you want to do an autoencoder over there. And the network size is actually much smaller than the original HDF data set, which means we actually achieve a really good, nice compressing of the data set. So one future directions is that we wanted to use these techniques to compress large, really large parametric turbulence data set. So for example, let's say if I have, if I want to study the effects of Reynolds number on some turbulence data set, and maybe I have 100 Reynolds number case, maybe I have 10 or 100 Reynolds number cases over there, but each spatial-temporal field might take gigabytes to store, and then I might be end up with maybe 1 terabyte data set I need to analyze. This is basically insane, and it's also basically insane to transfer. What if I can compressing all this by just training a big neural implicit flow over there? So why is that? Because let's say if the effects on the Reynolds number is not really that sensitive, maybe you don't really need 100 Reynolds number cases over there, maybe 20 or 50 cases over there, but you don't really need to find out which number it is. You just need to transform this huge data set into a single neural network, and the neural network will figure out if it trains well. It means if the compression ratio is really high, then it means okay, there isn't much fancy parametric variation over there. The signal complexity is not really that high in the data set. Then you can safely transfer this model, give this model to your colleagues, and these colleagues can easily analyzing and playing around with this data set to analyzing all those turbulence statistics with variation to the Reynolds number. So this task is actually pretty impossible for CNN, but however, it's kind of okay for implicit flow. But although I do have a really long training time, which I will show later. So as you can see, this is a 2D slices of the flow field, and the NIF performs pretty well in terms of fitting this data set. And here is the PDF statistics for velocity magnitude, as the gradients as well. And here, next, I want to have a more challenging task. I want to compare the Q criterions. And I want, because it's a higher order derivative terms. If I can fit this well, that means, okay, I did a good job in this. So, and then I colored with velocity magnitude, which also a high order quantity, high order spatial quantity. And as you can see, the left is the reconstruction, the right is ground truth. Almost there's not much visual differences as far as I can see. So I would call it a success. So next, the final task would be using this framework to perform data-driven sensing spatial field from sparse measurements. This has a pretty interesting. This will have many interesting applications if you want to do realistic flow controls, because you don't really have the measurements of the flow at every point. Usually we'll have measurements basically on the surface of the object. Then you want to infer what are the flow field above the surface, maybe far away from it, if the problem is like as simple as a flow of a cylinder. So here is in this task, I want to placing sensors on the sea of the Earth, and I wanted to reconstruct the sea surface temperatures of the Earth by using those limited sensor measurements of sea surface temperature at these sensor locations. This is actually a famous problem. The placement, how to placing those sensor measurements can be done by using PUD-Q-DYM. It's a famous technique in data-driven reduced model community. However, it's later leveraged by Steve Brunton and Nathan in their group about using this for like data-driven sensor placement. They choose a different name, but it's actually the same thing. So here I'm choosing the sensor locations by using PUD-Q-DYM. And then once I'm getting the sensor locations over there, I use the NIF to perform a regression to figure out what is the full field sea surface temperature data set. So I'm training for 16 years and testing for the next 15 years. So as you can see here on the top right, top left here, these two red figures are corresponding to traditional state-of-the-art methods, basically the PUD-Q-DYM methods. And the solid line is the training error. And when you're getting more sensors, the training error goes down, obviously. However, for the testing errors here, the number of sensors has a sweet spot over there. It's 5 sensors. This is actually a pretty bizarre and is also intuitive because the chaoticity of the sea surface data set. But it's kind of embarrassing because all that you need is 5 sensors, and the best is the best result you can get. It's pretty embarrassing. However, when we come using NIF and we increasing the number of sensors, we found that NIF actually can outperform can generalize better than a PUD-Q-DYM. So just look at these blue curves over there. Obviously, the solid blue curve converge much faster than the red blue the red solid curve over there, because we have our model is nonlinear, so we fit much better in terms of fitting the training data. We fit much faster than them. However, in terms of the generalization errors over here, just look at this plot in the bottom right, and we found that when we're having like more than 400 sensors, basically just a little bit more than 100%. Just more than 1% of the total available sensors, we can actually beat the best result for the PUD-Q-DYM. And these applications is not only has significance in terms of predicting the sea surface, but also has significance in terms of building much better reduced models, because PUD-Q-DYM is actually a technique in projection reduced model, sometimes called hyperreduction. So right now I have a nonlinear hyperreduction that performs better than the original linear hyperreduction. So it will be interesting to see like how much performance boost it can provide in projection reduced models. So next I want to talk about the challenges for NIF. This talk won't be complete if I don't talk about any drawbacks of my framework. It won't be complete. So the first one, the drawback of NIF, is that it is very expensive to train. For example, for 3D homogeneous isotropic turbulence case, it was 20 snapshots and it is 128 cubic resolutions, and it takes me like more than 165 hours using I think it's a 48 gigabyte NVIDIA GPU to train to get our final solution. But this is obviously still better than CNN, because CNN won't be able to train on that GPU card. So it's kind of problematic right now, but it's offline. So since nowadays everyone is thinking offline cost doesn't really count, then I guess it's not much a big deal, but it's still a kind of pressing issues if you compare these algorithm versus CNN and POD. So don't be surprised if it turns out you need a very good GPU to train like maybe 100 hours for your giant data set. But if your data set is like really simple, then it's actually converged pretty fast. As you can see here, the number of epochs it takes usually less than 100. But because of the nature of the problems here, because of the nature of the number of data points is really huge. Each epoch actually takes really long time. Since because the number of second issue is the number of data points is really huge because we flatten the large data set. So the data will look like, so the data set will look like a tensor product. This is basically the same issue shared as DeepNet over there. The last issue is that in practice, it needs small learning rate and the really large batch size. Sort of really, the large is sort of relative large. So basically, you need to filling up all your GPU memories to stabilize the training. So it means we need a good GPU, or we need some data parallelism solutions for the NIF, which will be the next. I believe it will be the next direction to go. So in summary, I just want to talk about the NIF-based framework outperforms state-of-the-art methods in data-fit, mesh-agnostic models, data-driven sparse sensing, and it is learning latent representation of high-dimensional data from arbitrary complex data set without unnecessary pre-processing loss over there. And the key idea of NIF is that it isolates spatial complexity away from temporal and chaos, temporal complexity, for example, chaos, and parametric complexity, for example, like bifurcations. This philosophy is following the same philosophy as the so-called low-dimensional manifold, categories in terms of learning models for in terms of learning surrogate model for PDEs. So basically there's like, as you can see on the right bottom figure here, there's three sort of families of methods. On the left bottom is mostly spatial invariant family of methods, like based on convolutional neural network proposed by PD, for example, the PDNet proposed by Yuping Lu and Zichao Long from Peking University. They are in Professor Dong Bing's group, and or the deep AR from Zabarak's group. They all use convolutional neural network as their main machinery. However, I want to mention that, for example, in the deep AR framework, the Zabarak's group, their highest resolution for their problem in 3D is 32 cubic. This is not because they cannot do higher, it's because the nature of the CNN is having a pressing issues, having a pressing limitations in their resolution over there. Several other new interesting framework, like graph neural operator framework. As I mentioned before, they also leverage spatial invariance over there. However, for a neural operator, the major issue is that you really need a sort of a square computational domain in order to perform the Fourier using the convolutional theorem to do the Fourier trick. For example, if you have a triangular domain, you cannot do this at all. However, we are basically following the low-dimensional manifold philosophy. It's bottom up. It originally from the POD, Gleichung ROM, Koopman, SPG, or data-driven closure, or more recently the CNMP ROMs. And on the other side is the physically informed neural network, basically mostly from Professor Johnny Konidakis' group. Basically, what they are doing is to using these this physically informed neural network. I forgot to mention DeepNet over there. Sorry about that. And basically, what they are mostly doing is using physics equations to solve. Using physics equation to solve the PDE problems. However, we are here, so we didn't use any physics information, and our only focus is on learning and data representations. So the take-home message here is with NIF, right now we can extend sort of the pure data-driven models to multi-scale flows on 3D arbitrary mesh. I think this concludes my talk. I think it's right about 15 minutes. And thank you for listening, and I'm happy to take any questions.
Yeah, thanks for Dr. Shaowu Pan to give such an impressive talk here. So we would like to take any question. You can just open your mic or hands up to ask questions.
Hi, Shaowu.
Yes.
Hi, can you hear me?
Yes. Nice to see you.
Hi, hello. Hi, yeah, I just only have like a nice talk first of all, and I just only have like one question. Yes. So I have some concern for like this framework to how to sense the boundary. For example, if your cylinder is moving in your domain, right? And how do you what's your plan to make this NIF framework to be able to sense the point is in the domain or is out of the domain? basically?
Yes, this is a very good question. So thank you for asking. So in terms of enforcing boundary, I guess you're saying that if I have unsteady boundary conditions,
Right.
let's say I have it's depending on time, but I know it before but I know it before running all the algorithms, right? Let's say if I know it, if I know it's a sine, oscillatory, trajectories, then one thing I can do is I guess one thing I can do is probably doing the old trick on the paper that we co-authored before.
I see.
Yeah. That's one way to do that. But in practice, I think if you're just doing a blind, black box using NIF, if you can guarantee that the mean square error is pretty small, the results looks pretty good, because the only thing I did here is just dimensionality reduction. It's not any kind of predicting, extrapolations. No.
I see.
Yes, it's just fitting the data set.
I see. Okay, great.
Thank you.
Any other questions?
Shaowu, it's like a very good talk, like very impressive. So coming from an experimentalist standpoint, and as well as oceanographic standpoint, as you show one case that's multi-scale, sparse sensing is really, really important. But in the real world, there's also a key importance of the noise. But the sensor noise is quite significant, and sometimes it's not it's actually sometimes it's not white noise, it's actually color noise. So in terms of uncertainty quantification, I know it's not a point for uncertainty quantification, but for uncertainty, and do you have any suggestion or try any noisy data, and what's if for these noise data, what's your suggestion to do that, to do the pre-processing, or there will be some generalization or dropout, or something during the training, or during some post-processing of the data?
Yeah, thank you, Professor Fan, for this interesting question. So I had for my framework, I haven't really adding any noise into the data set, but in terms of quantifying the noise in the data, so usually I had a paper on sort of the Koopman operators, where I used sort of the Bayesian deep learning framework to quantify the source of the uncertainties. So usually what I would so in that paper, what I did is using Bayesian neural network framework that I basically make sort of train when I was training this neural network. Each neural network weights and biases is not a deterministic quantity; it's become the distributions, and this distribution is because it's a really high dimensional distribution problems. High dimensional Bayesian inference problems. The thing I did is I used some Gaussian surrogates to approximating these distributions. This is called variational inference. And once I get infer, if I have a noisy data, and I can infer basically the distribution of these neural network weights and biases. And then once I having this, I can do some, doing uncertainty propagations of it. When I getting this model, I can running this model for 100 times by sampling those weights and biases in this neural network model. And end of this is just ensemble techniques for uncertainty quantifications. And when I was doing all of this, I getting pretty much good denoising performance over there. So another I guess in terms of denoising, this one of these ways to perform Bayesian sort of techniques. The other thing I believe is if you could getting some nice prior knowledge of the systems. For example, if you know that the ground truth is maybe multiple harmonics adding up together, but you don't know the frequency, you just know it's harmonics. You don't know the frequency, you don't know the phase, you don't know the amplitude, but you know they are harmonics, maybe less than 100 harmonics, and they are colored by, they are contaminated by many kind of noises over there. And then you probably can you can using framework like Koopman to denoising this data set. And actually there's a paper by by Hennings in our group. He did some testing cases that when he using his framework and under good prior knowledge that this system is composed of harmonics, and they achieved really good performance, robust performance against traditional algorithms like LSTM, TCNs. I think there are a couple of few other interesting algorithms, interesting deep learning time series framework over there. But I would say maybe a more holistic approach to resolve your problem is to embedding physics information inside to further reduce the noises over there. And for example, in particle, in PIV, in tomographic PIV, usually, there will be images for example, 4 images that was taken. Then you were getting you want to reconstruct the particle field from these 4 images. Then from this particle field at different time, you can reconstruct the velocity field. And one way in their field to denoising the noises is also actually to using governing equations to do that. I've seen quite a few papers on that. Also using these kind of techniques, and it achieved really good performance in terms of denoising. So maybe in that case, PIN will be a better approach to do if you know the governing equations, and you can perform some interesting, I believe, denoising using pins.
Okay, thank you.
Yeah, thanks for the long answer. But however, our time is running out, so we can take one more question here. If anyone has any concerns.
Actually, if there's nobody, I will ask one more question. I will just give a 10-second.
Yes, no problem.
Doesn't seem to be some people raise questions. So I will have a follow-up question, Shaowu, since you're talking about your past work in the Bayesian network, I assuming also the GP, a surrogate model, all the things. I don't know whether you have touching this topic because I was away for 10 minutes. So basically, there's also another thing is active learning, since you have sparse sensing, right? So I know this is a very intense training for 3D arbitrary mesh. The question is for let's say for a buoy, there's cases buoy can actually move in different location. Right now there's NOAA deploying movable buoy to for the ocean sampling. So are you consider or have the capability in the future that have ability say oh, I can put additional data there, or move my one sensor location to another location for better information fusion, for better data fusion for the information. So as basically actively configured sample spatial and temporal sample sensors.
Yes, I think this is thank you, Professor Fan. I think this is really an interesting suggestion over there. So right now I haven't think about that, but ultimately I want to use NIF for digital twins. And when I'm using digital twins, I need to updating the model with the data and which data I should use to improve them. To reduce the error further, it will be using active learning to see where I should, basically you have a surrogate, GP surrogate for the error surfaces, and you want to minimizing the errors based on some criterions, with some risk management, some concept over there. And it is interesting. I think it's possible to do, and it's definitely a path to take if I further pursuing this and applying to a real maybe a real experimental, combining with collaborating with experimentalists like you, that you can have data set generated at any time, and I can use this to efficiently collecting data set for my models. I think it's definitely interesting.
Yeah, I mean, it's just a thought process, but anyway, it's really interesting. I'm glad this is recording because I can rewatch again and maybe later ask more questions.
Yeah, thank you. We can definitely talk more if you want. Yeah.
Okay, so thanks again for Dr. Shaowu Pan to share his innovation idea here. So we'll end this seminar today, and we'll see you next Thursday. Bye.
Thank you, Professor Zhang. Bye.
So bye everybody.
Bye, everyone.